All right, hello. Thank you for joining us, everybody. I'm going to let Chris do introductions, and then we will get started with questions.
Okay, thanks everyone. Welcome. Seems like we have close to 200 people with us today, so that's great. It's a big crowd, but we're all socially distancing because you could be anywhere. I'm here in Tucson, and Southern Arizona is about to ease out of its lockdown. And meanwhile, we're ready for questions on astronomy.
Thank you. The first question is from Surya, who's on with us live, who would like to know more about blackbody radiation. So what is it, and why is it that matter under conditions of high pressure and temperature radiates like a blackbody?
So blackbody radiation refers to, it's a fundamental physics concept. It's any object which is in equilibrium with its surroundings, which is to say it's not being actively heated or cooled, its energy in and out flow is equalized, which has a particular temperature, and it's a radiation characteristic of that temperature. And this radiation spectrum was worked out early in the 20th century by the founders of quantum theory. The reason it's called black body is an experimental physics reference. When you want to create a pure black body spectrum, the easiest way to do it is to have a physical object like a metal cube or something with a cavity inside that's black, and radiation emerging from that cavity is equalized in temperature with the physical object, and so it has the blackbody spectrum. So the blackbody spectrum is a broad spectrum distributed over wavelength that's characteristic of a particular temperature. And as you increase the temperature of the object, the mean wavelength of the radiation goes down, or the frequency goes up. So hotter objects radiate at shorter wavelengths. Also, the total amount of energy, and it's called a Rayleigh-Jean spectrum, in fact, named after the two physicists who first characterized it. And that linear relationship between temperature and the peak wavelength of the blackbody radiation is called Wien's law. There's a second law called the Stefan-Boltzmann law, also named after two physicists, which describes the total amount of radiation from an object at any temperature as you raise the temperature. And that total amount of radiation is a strong relationship with temperature, going as the fourth power of the temperature. So if you take a particular physical object, it could be a star even, or a gas ball, or a solid object, or a liquid even, and you double the temperature, the amount of radiation from it goes up by a factor of 16. So these are the fundamental physics relationships for radiation from an object at a single temperature.
All right, thank you very much. The next question is from one of our live viewers. The question is from Alexis, and do galaxies have Lagrange points, sort of like our solar system does, and is it possible for a galaxy to get stuck in a Lagrange point of another galaxy?
That's an interesting question. It turns out no. Lagrange points are a concept named after a famous French mathematician of, I think, the late 18th century, who did a number of very important things in mathematics beyond working out Lagrange points. So it comes from orbital dynamics using Newtonian theory. And Lagrange points really only emerge in a three-body system. So they are sort of rough balance points in gravity. Two of the Lagrange points are stable, which means an object placed there will stay there. And two of the Lagrange points are unstable, which means that the forces are balanced at the Lagrange point, but any small perturbation will move the object away, and then it'll go away from the Lagrange point forever. So Lagrange points really only exist in a three-body system like Earth, Moon, and Sun. That's the typical Lagrange points we talk about, or any three-body system. Galaxies are big, messy objects with billions of stars and mass distributed in a sort of smooth way across large distances of space. So you can't actually construct or expect there to be Lagrange points for a galaxy, even external to the galaxy. So when you have multiple galaxies in space, their mass is so distributed that they don't actually create points in space that fit the definition of a Lagrange point.
The next question is from Monica, who's on with us live. or I'm sorry, I guess it's Tina. I am Tina, and I want to ask, what would happen if dark matter and normal matter collide?
Well, it probably happens all the time. Um, it depends on the situation and depends on the circumstance. If it's in space, in deep space, intergalactic, interstellar space, the interactions are just generally very weak because dark matter doesn't have electromagnetic interactions. So literally all that can happen between dark matter and normal matter is a physical collision. So it's an actual collision between the dark matter particle and the normal particle, whether that's a neutron, proton, or an electron. And in solid matter, that's the same situation. The dark matter only interacts mechanically by an actual collision. That, however, gives one of the ways that we're trying to detect dark matter. Because out in space, all that happens between normal matter and dark matter is they interact gravitationally, and typically dark matter is dominant, and so the normal matter forms pools, if you like, or puddles concentrated within larger, more diffuse halos of dark matter. That's what galaxies do, and on all large scales in space. But when we're trying to detect dark matter, we can use the fact that it has a physical impact with normal matter. And so the way dark matter detectors deep underground are configured is you have a very pure substance, typically a semiconductor, and you look for collisions of the dark matter particle, very occasional collisions with the normal matter in the lattice of the detector. And since they're not going to release light or radiation because there's no electromagnetic interaction, literally all that's released is mechanical energy. In physics terms, these are called phonons, but it is an energy release, and it can, in some detectors, be converted into radiation or energy that you can detect. So it's by these collisions in detectors and deep in mines on the Earth that we actually hope to find out what dark matter really is.
The next question is from the Wizard of Hogue, who's on with us live. Is there a simple explanation, or can you please explain simply the kind of the underlying or key concepts of string theory, and what's the current status of string theory in the astronomical or cosmological community?
I'll obviously have to give an abbreviated answer because it's such a huge subject, and it is very mathematical and abstract in essence. But the idea of string theory comes from the concept of unifying the forces of nature. So recall that in physics, in the late part of the 20th century, one of the great successes of high energy physics was to show that the weak in the electromagnetic force, that is the weak force that causes radioactive decay, and the electromagnetic force are actually versions of the same thing. And so in accelerators of sufficient energy, those two forces were shown to be part of a single electroweak force, unifying two of the four forces of nature. That was an incredible success, and of course, extrapolating from that, physicists imagine that there is an uber force, an Ur force that underlies all the four forces, and if it could be realized at sufficient energy, you could see that they're all the forces we see as distinct or manifestations of the same thing. So string theory is a theory that attempts to reach for the underlying theory of that unification. And the only way it can get there, of course, is to go to energy scales and physical size scales that correspond to extrapolating the force diagrams to the point where they're all unified. And that is an incredible temperature, 10 to the minus 32 seconds after the Big Bang, or 10 to the 35 Kelvin. And also incredibly small size scales, far, far smaller than the size of an atom. And in the theory, the fundamental entities that underlie particles are strings. So instead of particles, the way we might think of them as little BBs or marbles or three-dimensional objects, we have one-dimensional energy objects that are called strings. And it's the vibrations, oscillations, collisions, mergers, and splittings of these strings that represent all the particle interactions we see in the everyday world. But these are the underlying entities responsible. So string theory is audacious because it reaches to an experimental regime far beyond our capabilities now, or really in the near future, or any time we can imagine, which means that testing string theory, of course, is extremely difficult. It's really beyond our capabilities now. So it's a theory. It's elegant, it's beautiful. It almost always involves 9 or 10 dimensional space-time. So these one-dimensional strings are entities that exist in a larger landscape of space-time dimensions, that's part of the theory. There are different variations of string theory. So string theory is not really one thing. And in the 1990s and the 2000s, theorists working on string theory realized that the string theories they'd been working on were individual examples of a larger landscape of theories that are now called M theory, M for membrane being a higher dimensional object than the 3 dimensions of space-time we see. So this is a very active area of theoretical work, but it's not translating into experimental research because so far there's no way to test string theories. Calculations are very difficult. New mathematics had to be invented to operate in string theory, and the jury is really out on whether it's a successful or fruitful way forward for physics. The idea of grand unification of the forces is still on the table and viable, and physicists think that there is some progress there. But string theory, as a specific example of a research project, has been very slow to progress, and some people are turning away from it, actually. There's a backlash about string theory in many physics departments. So it's not got as many people working on it, I would guess, as it did about 10 years ago.
Thank you. The next question is from a couple of different viewers who are on with us live. Alexander and Dennis both have asked questions about comets from the Kuiper belt or the Oort cloud were probably deflected from their orbits by the gravity of passing stars, from what I understand. How close must a star be to exert this influence? When did this happen? And are there stars around us that might have caused this effect recently or might in the future?
Yeah, so those are 2 different regimes. The Oort cloud is very far away from the inner solar system, the 40 or 50 astronomical units where the major planets sit. The Oort cloud extends 50 to 100,000 astronomical units, so really a long way out. And that's a significant distance. That's a significant fraction of the distance to the nearest stars. And so it's well understood how a fairly nearby passing star, if it comes close enough to the solar system, absolutely doesn't have to get nearly close enough to come into the solar system as we know it, the giant planets. But if it just nudges or gets close to or perturbs the Oort cloud, then that perturbation or that nudging will send a cascade of comets out of their normally highly elliptical orbits, many of which will go into Earth crossing orbits. So it'll basically jostle the Oort cloud into sending a cascade into the more inner regions of the solar system. And in the modeling, that can occasionally result in impacts on the Earth. And those, of course, could be catastrophic. They could be mass extinction type impacts. So the passage of a nearby star is understood to be a potential cause of mass extinctions or dramatic events in the Earth's history. This is unlikely to happen in the inner part, in the Kuiper belt. That was the other part of the question, because that's about 40 to 100 astronomical units. So that's not very far outside the normal planets. And then passing stars just don't get close enough to the inner solar system to really perturb the Kuiper belt. But the Oort cloud definitely, and the modeling suggests, given what we know about the density of nearby stars and their trajectories in 3-dimensional space, that every 50 to 100 million years, a star may come close enough to our solar system to, disturb the Oort cloud and cause major devastation potentially to the Earth. And that's interesting because that roughly corresponds to the time between major extinctions in the Earth's history. We can't physically associate a passage of a nearby star with any mass extinction on the Earth, but it's fair to point out that there are a couple of mass extinctions that don't have an obvious cause. The obvious causes are an impact where we find the crater and debris left over, or a large geological event where we can date the geological event. So there are some extinctions that haven't had a smoking gun attached to them in that way, and maybe they are caused by this interaction.
Thank you very much. The next question is from Daniela, who's on with us live. How long does it take for a star to fade away?
Well, as the white dwarf, it essentially almost takes an infinite amount of time. Most stars are of low enough mass that they will die as white dwarfs. That's the class. Most stars are the sun's mass or quite a lot smaller, and any star of the sun's mass or smaller will die as a white dwarf. So in that final phase, the star is basically a very high density cooling ember, sort of carbon-rich ember. And it just radiates heat into space and just gradually cools off, and it's a very slow process. So in principle, to go to 0 Kelvin, it takes an infinite amount of time. But over some period like tens or hundreds of billions of years, white dwarfs will cool to become black dwarfs, as we might put it. So they aren't obviously putting out visible radiation anymore. The normal white dwarfs, soon after they form, the kind we can see in our own galaxy, actually are quite hot. They have temperatures of tens of thousands of Kelvin, 40, even 50,000 Kelvin. So it takes them quite a while to cool down to the point where they're invisible.
Excellent. The next question is from one of our live viewers. Ramin would like to know, how old is the Earth and how do we know?
So the Earth is 4.54 billion years old, and the error, the uncertainty in the Earth's age is in that third significant digit. In other words, we know the Earth's age to an accuracy of about 1%, maybe 2%. It's very precise. And the reason we know it is from radioactive decay. So it's a pretty standard method in geology and also used for dating living organisms that have died and fossilized to look for various radioactive isotopes where we know what the half-life is. And if we can guess what the initial composition of the rock was when it was formed, and then we look at the relative composition of the parent isotope, that is the heavier isotope, and the one that it decays into, the daughter isotope or the lighter one, then we can just trace radioactive decay, which is an exponential process, and simply calculate the age of that rock. And so that's been done fairly reliably for old rocks on the Earth. The difficulty on the Earth is finding really old unaltered rocks, because most of the rocks on the Earth have been in and out of volcanic situations and metamorphosed, and so their original state has sort of been lost by pressure and heat over time. But there are old enough unaltered rocks that we can apply this method, and so that's where the age come from. And a cross-check of it, which is actually even more reliable because the object has had a simpler history, comes from moon rocks. So we brought back about, Apollo astronauts in their various landings brought back about 450 kilos of moon rocks, almost all of which are held in a deep biohazard level 4 containment facility at Johnson Space Center in Houston. And those rocks, because the moon is not a volcanic object, the moon was formed coevally with the Earth, and so the age dating of moon rocks is even more reliable than Earth rocks, and it gives the same number. So we're very sure of this age.
Excellent. Thank you very much. Oh, yeah, excellent. Thank you very much. The next question is from Dimitri. We'd like to know, what do you think about the potential for using quantum entanglement of photons and electrons in astronomy? So things like quantum teleportation and quantum communication.
Well, quantum entanglement is now moving out of the lab. It's actually potentially going to start becoming used in commercial products. That's probably looking 10 years out. Quantum computers is the first way we'll see this. So quantum entangled states are a different way of holding information. And instead of the binary digits of a digital computer, gates and switches, in a quantum computer or quantum states, we hold the information probabilistically, and we can combine the information probabilistically. And what that does in a computational sense is it turns a quantum computer into a very highly parallelized computer, and so it makes it very efficient. That's the upside. The downside, of course, is that maintaining coherent quantum states that are entangled for a significant number of atoms is really hard. So quantum computers, as I recall, only have got up to about 100 or 200 coherent quantum states in different atoms. That's small scale. That's not anything like going to approach the computers we have now. So that's where quantum entanglement is probably going to have its first play, is into parallelized computing, because that's a huge market and there's a large amount of profit to be made by doing that. In other astronomical terms, it's not clear what the applications might be, but quantum entanglement has now been demonstrated on intercontinental scales. Very exciting. As recently as 10 or 12 years ago, quantum entanglement had been demonstrated over distances of a few meters in the lab, but now people have used split light beam experiments to show that you can have coherent entangled states transmitting information or holding information across distances of thousands of kilometers, which is very exciting.
The next question is from Damir, who's on with us live. Is our sun gravitationally bound to the supermassive black hole in our galaxy center? Is our sun affected by, never mind, or is our sun affected by dark matter gravity is the part of the question.
Right, so what dominates on a larger scale, what dominates the sun's situation in terms of gravity? It's a good question. So we can actually rule out the supermassive black hole at the center of our galaxy because that has a mass of 4 million solar masses, 4 million times the mass of the sun. Now that sounds large, but it's 28,000 light years away. And if you draw a box around the central few hundred light years of the galaxy, that has a very dense star cluster that contains far more than 4 million times the mass of the sun. In other words, in the central regions of our galaxy, normal stars outweigh the central black hole by orders of magnitude, a couple of orders of magnitude. So the sun is not really being held in its place in the galaxy by the black hole at all. If anything, it will be the normal stars. But on the larger scale, of course, it's not even the normal stars, because when you trace the rotation of our galaxy moving out from the center, you find that at the sun's distance, if there were no dark matter in our galaxy, the sun should not be orbiting the center of our galaxy as rapidly as it does. The sun orbits our galaxy every 240 million years, so it goes around about 4 times every billion years. And according to Newton's law of gravity, if all the galaxy was made of was the stuff we see, the sun would not be moving that fast. So we have to infer a large amount of dark matter. And at the sun's distance from the center of our galaxy, that dark matter dominates the normal matter by a factor of 6 or 7. So the true answer to the question of what holds the sun in its orbit of the galaxy is dark matter, and by a long way, actually, because dark matter is the dominant material in the galaxy. Now, that wouldn't be true if the sun was right at the center of our galaxy, because at the center of our galaxy, the density of normal matter in the form of stars is so high that the dark matter density is eclipsed by normal matter. And so a star near the center of our galaxy is actually held in its orbit by normal matter and all the other stars there. But out where we are, it's dark matter.
Thank you. The next question is from Ayush, who would like to know, what is the significance of antimatter? What is it made up of, and why is the universe made up of matter and not antimatter?
So there are sort of 2 questions. I'll answer them separately. What is antimatter? And then what is the reason for the universe being entirely made of matter, almost entirely made of matter and not antimatter? As a physics question, antimatter is essentially a set of shadow particles, if you like. I'm using that term loosely, metaphorically. A set of shadow particles that have opposite quantum properties to normal particles. So for the proton, you have the antiproton, and an antiproton will have opposite quantum properties. And that includes electric charge, but it also includes spin and other quantum properties. For the electron, there'll be a positron, which is obviously positively charged, but it's also got opposite quantum properties in other senses too. And since the masses are identical of antimatter and matter, the mirror particles, what matters is what happens when they come into contact and they annihilate with the production of pure radiation. So the mass of the combined particle and antiparticle is converted by E equals mc squared purely into radiation. So in quantum theory, antimatter and matter have equal and opposite properties, and they have equal status. So if you had pure energy in the lab, and this happens, we can make this happen at will with a physics experiment, you can create equal numbers of particles and antiparticles, and that's how they're made. So we see the symmetry between matter and antimatter in the lab, and that's what physics says. Now, the question of the universe and why the universe is overwhelmingly made of one of these two forms rather than the other, it comes down to what happened early in the universe. First of all, experimentally, we can say very conclusively that the universe is made of matter and not antimatter. If we create antimatter in the laboratory on Earth, it disappears almost immediately because it runs into matter and annihilates into gamma rays. So if there were antimatter around, it couldn't get very far before running into matter and disappearing. So we know there isn't antimatter on the Earth. But we actually know that even beyond the Earth, because even if there were anti-stars scattered through the Milky Way or anti-galaxies scattered through the universe, the interfaces between these objects, even though space is mostly empty, would lead to sufficient gamma ray emission that we would see it with our satellites. So antimatter in the universe has actually been ruled out since the first gamma ray satellites were launched in the 1970s and 80s. So the universe is matter, and we're left explaining why. And the best answer so far has been that out of the symmetry of forces and the grand unification of the three forces, except for gravity, there was a slight asymmetry that resulted from the breaking of that unification. And that slight asymmetry gave rise to a very slight excess by about 1 part in a billion or a few parts in a billion of matter over antimatter. And in the early universe, when the universe was very hot and dense and particles and antiparticles couldn't go very far without meeting each other, as it expanded and cooled, those particles, an almost equal number of antiparticles, but slightly less, annihilated, and the small residue left over became all the matter in our universe. And since they were almost equal in quantity and most of them turned into photons, that suggests that the universe should be made mostly of photons and not particles, by a factor of a few 100 million to 1, and that's what we see. Now, that's not a prediction, so that's an explanation of something that we observe. However, the nature of this asymmetry and where it arises from in physics is still not understood.
All right, thank you very much. The next question is from Rose, who would like to know how much or does the expansion of the universe affect time?
Well, time is affected by local gravity. So what we understand about time from general relativity is that the way time flows depends on gravity, depends on local gravity. You can define clocks in an expanding universe, and they will indeed be subject to the local gravity, where the stronger the gravity, the slower the clock runs. Now, in our old expanding universe, the gravity in a particular situation is not changing very significantly. So time, we cannot observe this change in the rate of time flowing in the present universe or by any experiment that we can do. But in principle, time is coupled to the strength of gravity in an expanding universe. And that's a prediction of general relativity, but it's of course very hard to test in the early universe because we have no direct evidence reaching us from those times that involves a time measurement.
Excellent. Thank you very much. The next question is from Carlo, who is in Italy and would like to know more about gravitational lenses. Can you explain more about how that works?
So lensing was a prediction of general relativity from right after the theory was published in 1916. Einstein wasn't sure this would ever be observable, but there were other theorists in Europe who saw that it was very interesting, and they wrote papers about it early on, before 1920. And the real problem was nobody imagined how you could see this effect. So it wasn't until the 30s that some physicists and astronomers decided that you might be able to see lensing, that galaxies themselves were sufficiently massive that if there was a more distant galaxy behind them, it's possible that they could lens the light of a more distant object, in which case we'd see the background galaxies light altered, distorted, magnified or demagnified possibly, or split into multiple images. And so that prediction was made, and it took a while to observe. In fact, it was first only observed in the form of quasars, very compact objects at very large distances. We saw multiply image quasars. I think 1979 was the first, the double lens quasar discovered actually at the Mount Hopkins Observatory where I work. That was the first evidence that lensing occurs in a quasar. And then galaxy lensing was discovered soon afterwards. And when the Hubble Space Telescope was launched, we started to see lots of examples of it because of the sharp imaging. So gravitational lensing was a prediction that was pretty much out there for decades before anyone actually observed it. And it's directly analogous to an optical lens, except in this case, gravity is the lens.
All right, the next question is from Raphael, who's on with us live. Why is it that all of the planets and well, it says galaxies, but maybe spin clockwise?
Right. So I think the question refers to planets. So the planets all spin. That's not completely true because Venus is the counterexample. But in general, in the solar system, all the objects spin in the same direction, which means their angular momentum vectors point the same way. And they spin in the same sense that the sun spins at the center. So the angular momentum of all the objects that formed in the solar system is consistent. They're all consistent. And that's because all these objects form from the same diffuse, slightly rotating gas cloud that was much bigger than the solar system is now. So this is easy to understand in simple physics terms because that collapsing, slightly rotating gas cloud amplified its rotation, collapsed preferentially along the poles, and you end up with a disk of rotating material which has angular momentum, and that disk eventually forms the planets, and the material that's left over is blown away by the young star. So you expect to have all the planets rotating, spinning in the same way that they orbit the central star, and in the same sense that the star spins. Venus is the exception because it counter-rotates, goes in the opposite direction, retrograde rotation, as we say. And it's imputed that that was caused by a collision very early in the solar system history because there's no logical way Venus could have formed that way. It's sort of counter-physical for it to have counter-rotated. So we have to ascribe its counter-rotation to some impact or some interaction after the formation.
The next question is from Claire, who would like to know, can you explain why you would expect to observe infrared radiation from a Dyson sphere? So it's kind of follow-up from some of our earlier discussions.
Mm-hmm. Right. So the Dyson sphere is an energy trapping structure that a civilization has supposedly built around a star to be more efficient in their use of energy, remembering that the Earth intercepts about 1/billionth of the sun's energy at its distance from the sun, and we utilize a tiny fraction of that. So as a civilization, we're using a very, very small fraction of the sun's energy. If you had a higher energy requirement or wanted to be more efficient or had higher levels of technology, in principle, you could construct an energy trapping structure near a star right around it, essentially capturing the energy that goes out in all directions. Now, the reason that would radiate in infrared is because the star's radiation is going to be visible radiation, just imagining it's a star like the sun with an effective temperature of 5,000 or 6,000 Kelvin. But as it moves out from the star, it of course dilutes in energy. And so when it hits a physical object, that object will re-radiate at a lower temperature, and that lower temperature corresponds to infrared radiation. We can see this on the Earth because the sun is at a temperature of 5,700 Kelvin, and the Earth is at a temperature of about 370 Kelvin. And so the Earth radiates heat with that effective temperature, whereas the sun is more than 10 times hotter and radiates visible energy. So any object catching starlight and then re-radiating it will re-radiate it or degrade it to a lower or longer wavelength and a lower temperature, and that's why it would be infrared radiation.
The next question is from Dan, who's on with us live. What are your thoughts on the existence on Planet 9 as put forth by Mike Brown at Caltech?
Well, there's a strong possibility that there's a Pluto-sized or even larger object, beyond the orbit of Neptune and Pluto themselves. If it were in the Kuiper belt, which is quite a large amount of real estate, Kuiper belt formally goes from about 40 to 80, maybe 100 astronomical units. So, double the distance, more than double the distance to Neptune. That's a large amount of space to search through for a small object that far from the sun. And so these surveys have been going on, and they're still a few years away from completion. So hypothesizing a planet 9 is completely plausible because we've already found a handful of objects that rival or perhaps exceed Pluto in mass, and we haven't finished searching. So I think it's just a matter of time to either find a planet 9 or rule it out.
Another question on here, Ramin has asked, I don't know that we've covered this before, it's actually one of the most straightforward questions. Why is it that the sky is blue?
Okay, it's a good question, very basic about the sky and astronomy. The answer is a phenomenon in physics called Rayleigh scattering. It's to do with the fact that the aerosol particles, both the air molecules and the other aerosols in the air, the air is not simply oxygen and nitrogen mostly. It also includes very small dust particles. It includes other molecules. It includes water vapor particles of different sizes. So there are a bunch of aerosols and gas molecules in the air. A characteristic of radiation when the particle doing the scattering of radiation are very small is that it more efficiently scatters blue radiation than red radiation, short wavelengths, because that more closely matches the tiny particle size. The wavelength more closely matches. And so when light passes through an atmosphere of a planet like our own, the red light will tend to either pass straight through or potentially be absorbed, and the blue light will be scattered. And scattering means it will be deflected or re-radiated or deflected in all directions from its incoming direction. So if we imagine the sunlight passing straight through the Earth's atmosphere, the red rays from the sun will be mostly undisturbed and come to us directly, while some fraction, not all, of the blue rays will be scattered in all directions, and this happens throughout the atmosphere. So basically, some part of the blue light of the sun is being subtracted from the incoming sun's radiation out in space and distributed through the entire Earth's atmosphere. And hence, when you look out in any direction, you see that blueness. And the sun, of course, is made slightly redder than it would really be by that, because the red light comes through undisturbed. So indeed, if you went outside, and this has been done, of course, because we've had people in Earth orbit and we measured the sun from Earth orbit, the sun is indeed slightly less red as seen from above the Earth's atmosphere than it is on the Earth's surface. So it's sun's rays being scattered through the atmosphere.
Thank you very much. The next question is from an email. Christina Vislapu would like to know, what are other radioactive dating methods apart from carbon-14 dating? Could you explain how they work and where they're applied? And there's sort of an astronomy connection, to this.
Right. So radioactive carbon dating, the characteristic timescale that you can measure with a radioactive isotope is key to its half-life. So typically, you can only measure accurately an age which is some small number, some small multiple of the half-life. And so radioactive carbon, that half-life, I don't remember the exact number, is a few thousand years. So you can measure ages of 5, 10, 15, 20,000 years, the length of human civilization, essentially. If you want to measure the age of an old rock, that's significant length of the age of the solar system, you need a material that has a half-life of billions of years, because we think the ages are billions of years. The universe is 13.8 billion years old, Earth 4.5. And so we use either uranium or plutonium isotopes that have half-lives in that range. So by judicious choice of radioactive isotopes, you can find half-lives that range, actually there's some that are very long, like hundreds of billions of years, but typically you don't want them that long, because that's longer than the age of the universe. So you find uranium or plutonium will get you the billion-year timescales. And then there are other isotopes. Iodine, for example, is one. There's radioactive iron is one, where you can measure timescales of like tens or hundreds of millions of years. And then when you get to shorter timescales, you're looking at different isotopes, and then carbon gives you the short timescale corresponding to human civilization. So you use the tools appropriate for the job, and then you can measure pretty much any timescale you want.
Excellent. Thank you very much. See, the next question is, in your opinion, what has been the biggest achievement in astronomy in the past decade?
I think it's pretty clear that the biggest achievement in the last decade is down to the Kepler satellite, and it's the discovery of hundreds and hundreds of Earth-like exoplanets, pretty much all the work of one satellite. So Kepler, I think, was launched in 2008 or 2009, started taking data in 2009. So pretty much that's still within the last 10 years. And so during that time span, Kepler's stopped taking useful scientific data now. But for that decade, the news stories were dominated by the discovery of much smaller planets than we'd been able to detect before. So that was a dramatic discovery of the last decade. And I think the only rival to that discovery, of course, would be the detection of gravitational waves in 2015 and 2016. They're almost equally important. It'd be hard to choose between them.
So Shishir, who's on with us live, would like to know if can there be multiple singularities at the center of a black hole?
Not individual singularities, but in the theory of black holes, if a black hole is rotating, then the solution suggests that the central point-like singularity actually turns into a one-dimensional ring, if you like. That is a ring with no thickness. That's why it's one-dimensional. So the theory does allow for singularities turning into rings, and they're interesting. In general relativity, they're time-like curves, which means in principle, if you're inside the black hole exploring that extended singularity, you could travel backwards and forwards in time at will by moving along the singularity, assuming you could survive the experience, just a hypothetical. But there's no situation that we know of where black holes have more than one point-like singularity. That doesn't seem to happen in the theory, and we think also it doesn't happen in nature.
Excellent. Thank you very much. The next question is also from one of our live viewers. Let's see. They would like to know, how is it that we know that the cosmos is expanding, as opposed to something like it's collapsing towards a huge central black hole? Wouldn't that produce the same kind of motion effects?
We see the expansion in the observation of the Doppler shift. So, and it's a cosmological redshift rather than a Doppler shift, because Doppler shift is what applies in the lab or on a terrestrial scale. So it is actually a distinct physical effect. So we infer the expansion from the fact that the light from distant galaxies is redshifted. And the further away the galaxy, the more the redshift. That's a linear relationship in the local universe. That's the Hubble law. And the simplest interpretation of the Hubble law is that the waves of radiation that come from galaxies are being stretched by the expansion of the space through which they travel. So if you imagine an invisible three-dimensional grid that marks out distances or lines of constant distance in 3 dimensions, then the photon that travels to us at 300,000 kilometers per second is being stretched because the wavelength of the photon is referenced to space-time, and space-time is expanding. So that's a theoretical interpretation of the observed effect of the redshift. And since we see the redshift rather than blue shift, if the universe were collapsing or crunching down to a point, we'd observe the opposite. We'd observe, as you went further out from the Earth, the light of galaxies would be blue shifted. That's not what we observe. So we clearly observe an expansion. And in the theory of the expanding universe, that interpretation is expanding space-time. So that's quite profound, because space-time is invisible. It's mathematically called a manifold. And so we're inferring the expansion of something that you actually can't see, where the markers of that something that you can't see are galaxies themselves and the radiation that we see from those galaxies.
Excellent. Thank you very much. The next question is from Marta, who sent an email. How many spacecraft are there at the Lagrange points of the Earth, and how many more could we possibly put there?
At present, I don't actually know how many there are because that number does change. We launched more missions there, and some of the obsolete old missions that are defunded or obsolete, their instruments have died and they're past their lifespan. They actually drift away from Lagrange point. So Lagrange points we use in the Earth, Sun, Moon balancing act are the unstable ones. So if you don't do anything, eventually the object moves away. I think historically, I've seen a list somewhere, about a dozen space gave exquisite measurements in the microwave background over about a decade, the first decade of the 21st century. WMAP was at the Lagrange point. The next obvious big mission to go there will be the James Webb Space Telescope. The trick of the Lagrange point mission, of course, is it's unserviceable. In low Earth orbit, the Hubble Space Telescope has been serviced 5 times and still alive after 30 years. The James Webb will be unserviceable because that's a good chunk of 1 million miles away, and there's no way we could send astronauts there. So Lagrange points have advantages for space missions. The radiation environment is very quiet, far from the Earth. You can shield from sun's radiation, but you have a disadvantage, which is that if something goes wrong, you can't fix it.
All right. The next question is from Arthur, who sent an email, who would like to know if you can please explain the concept of redshift versus blue shift. Why are they different, and why is one shifted blue and one shifted red?
So there are 2 regimes of redshift and blue shift. One would just be an experiment that we would do on the Earth in a laboratory or inside the solar system, for example. If you shine radiation towards something while you're moving towards it, that light will appear redshifted relative to if you weren't moving. And if you're shining light at an object while moving away from it, that light will appear, I think I've got that the wrong way around. If you're moving towards it, it'll appear blue shifted, and if you're moving away from it, it'll appear red shifted. And you want an intuitive way to understand that. That's because as you're moving towards something, you're emitting a series of waves with crests and troughs and wavelength, and you're essentially catching up with your own waves. So you're sort of compressing them, and the shorter wavelength is bluer. Whereas if you were emitting waves while moving away from the object, you're running away from your waves and stretching out their wavelengths and therefore making them redder. So that's an intuitive way to understand it. Now that's in the solar system or a lab experiment. That's the Doppler shift. In cosmological terms, it's caused by the expansion of space-time. And there is no analog of a redshift to a blue shift because we have no situation in the cosmos where we see space-time contracting. And so we've never measured a cosmological blue shift, only redshifts.
Excellent, thank you. The next question is from Bill, who sent an email. I'd like to hear your views on the discovery from 2013 by the Planck satellite of a very cold region in the microwave background radiation. Is this a real observation? Is it an artifact? What could cause something like that?
The question could refer to a couple of things. The Planck satellite was the successor to the WMAP mission of NASA. Planck was an ESA satellite designed to look at the microwave background radiation with exquisite accuracy. I think it worked at 5 different microwave frequency bands and made exquisitely accurate maps with an intensity accuracy of about 1 part in 10 to the 5, or even a bit less. And of course, it expected only to see the fluctuations at that level that correspond to the seeds of galaxy formation. So anytime you'd see a larger global effect, like a hot spot or a cold spot, that would be interesting and telling. And in cosmology, you don't expect to see anomalies like that. The universe is supposed to be the same in every direction. And that's the isotropy assumption, which is generally verified. So there were a couple of times where Planck saw cold spots. It never actually saw a hot spot that was sufficiently anomalous that people got excited. The reason why you might see a cold spot that's got nothing to do with cosmology being an error or having a problem is that there are a large objects in the universe, clusters of galaxies, and these clusters of galaxies have extremely hot gas, hot plasma, temperatures of millions of Kelvin. And that hot gas can actually deflect microwaves, interact with microwaves in a physical process that scatters those microwaves away from the sight line and then leaves a deficit of microwaves in the direction of that cluster. And so that would look like a cold spot. And so if you have extremely large, extremely massive clusters of galaxies, you can definitely expect to see cold spots in the microwave sky. And I think some of the press releases and intense interest in the Planck data resulted from finding such objects. They're not a problem in and of themselves, except that if clusters form of too large a mass too early in the history of the universe, that's a problem because in gravity it takes a long time to form a cluster of galaxies. And I know that one of the clusters that was found seemed to pose a problem for cosmology, but that problem is largely abated.
Excellent. Thank you very much. The next question is from Philippe, who's on with us live, who would like to know if black holes grow in size when mass is added, then why is it said that a singularity is a single point of infinite density? How could that possibly get bigger or smaller?
Right, that's a good question. So the global mass of a black hole grows according to the mass that falls into the event horizon. So when we measure the mass of a black hole, we're essentially just putting a number to the mass enclosed within the event horizon, and that's just an area that we can't see inside of. So it's just a global number for the mass. Now the mass distribution within the event horizon is a more uncertain thing because that relates to the theory of black holes. And the theory of black holes does indeed suggest that there's a cusp of density, that it goes infinite at the center. And really, since we don't understand singularities in general relativity, they're anomalies, they're mathematical anomalies, there's no real way to ask or answer the question about what happens as you add mass to a black hole. Does it affect the singularity itself? Because the singularity is already an anomaly, and adding some mass to the black hole and possibly more of that mass going into the central cusp, it doesn't really mean anything physically because it's an infinite mass density anyway.
Excellent. The next question is, can you talk about what the difference is between a black hole and a white hole? People are curious about what's on the other side of a black hole, those kind of things. Can you talk a little bit about how that works and, sort of where some of this terminology that people hear in science fiction comes from?
Sure. Now, again, I'll answer that as sort of two different questions. What's on the other side of a black hole? That's easier to answer because really there is no other side to a black hole. A black hole is a rift in space-time in 3 dimensions. And since all we experience are the 3 dimensions, up, down, and sideways, there's no interpretation of another side. That is the space-time we occupy, and it's essentially a rift in that 3-dimensional space-time. So it doesn't have to have another side. The other side, asking about another side would infer yet another dimension that we don't know exists. The question of white holes is up for grabs, basically, theoretically. It is possible that in a large universe with where space-time had a complex structure, and the space-time was not smooth and linear, which is what we tend to see in our universe now that it's old and cold. If space-time were more convoluted, it would indeed be possible that space-time could be pinched between 2 different locations. So you could have 2 very different physical locations that were conjoined due to the curvature of space-time. And that's probably the scenario by which you could imagine a black hole in one part of the universe having a counterpoint in a white hole in another part of the universe, where the mass and the energy that went into the black hole in one part of the universe is actually coming out in a different location in the universe. So that's a very sort of schematic description of what a white hole might be like. And that's even a scenario that's allowed for in general relativity. So there's not science fiction in the sense of being against physics. The question of whether they exist in our universe and are observable, those are different questions. And as I've mentioned, the universe we live in tends to be rather simple, and space-time is not convoluted. So there don't seem to be any of those situations where space-time is folded or corrugated or interconnected enough that you might expect a white hole to form. So we don't expect it on those grounds. And then observationally, we've not seen anything that would suggest a white hole. You might imagine it's hard to sense a white hole, because how would you distinguish that from a star or any other place that energy was coming out? And I think the way you distinguish it, of course, is because it would be physically very small. It would be, again, the size of an event horizon as opposed to the size of a star.
The next question is from William, who sent an email. And his question is, why is it that spiral galaxies are spirals and why are elliptical galaxies elliptical? What causes different galaxies to have different shapes?
The first part of the answer, the historical answer was just this first part of the answer I'm going to give, and it's become more complicated recently. The first part of the answer is due to initial conditions. It's the fact that in the early universe, very large gas clouds formed by almost spherical collapse, and in that spherical collapse, you form stars very efficiently. The gas is all removed because it goes into stars, and those stars just take elliptical orbits and then gradually age and redden. And that's pretty much the description of an elliptical galaxy. It's old red stars with not much gas and dust in a quasi-spherical shape, because that reflects the original configuration before it became a galaxy. In the alternative mode of galaxy, early in the universe or perhaps later in the universe, a rotating gas cloud is spinning fast enough that it collapses into a disk formation. And in that disk formation, the star formation happens more slowly and steadily. So you don't simultaneously get one set of stars forming and then evolving and reddening and dying forever. You get a disk of gas and dust that's forming stars continuously, and those stars are getting old and redder, but new stars are forming from the gas. And that describes the Milky Way. The Milky Way does have a spherical cloud, a halo component. So there's an elliptical galaxy-like component to every spiral galaxy called its halo. And the halo actually has most of the mass of the galaxy in dark matter. But the visible stars are in this dominant disk, and that's because it formed later and more continuously. And indeed, in our galaxy, we see stars much older than the sun. The sun is about a third the age of the galaxy, and there are obviously stars still forming. So that's the basic answer. The more complicated answer, while we know that one galaxy doesn't directly turn into another type, galaxies have grown over time. So small galaxies have grown into larger galaxies, and in some of these collisions and mergers, they do change their type. So we know from simulations that you can have large spiral galaxies that collide, and 1 billion or 2 billion years afterwards, the merger product starts to look like an elliptical galaxy. So there are circumstances where you can produce an elliptical galaxy from the collision of two spirals. The spirals, we do believe, have grown from the consumption of smaller pieces, have grown from dwarf galaxies. And we can see dwarf galaxies being consumed by the Milky Way right now.
All right, Chris, so it's just after 1 o'clock now. It's like 1:02, so we'll go with one more question, and then we will wrap up for today. The final question is from Laura, who's on with us live. Why does light travel in the first place? Why does it move and not stay in one place?
Well, that's an interesting question. I mean, in physics, there are standing waves. So just to take sound as an example, sound is an example of a wave. It's a transverse wave. It's a longitudinal wave that moves air molecules on the Earth and any other place with an atmosphere. So in sound, you can have sound that travels through the air or any other medium from A to B with a particular speed. Or you can set up a standing wave, so a sound wave that just doesn't go anywhere at all. So it is certainly true that other kinds of waves than light have the possibility of moving at some velocity in a medium or not moving anywhere and being sort of standing oscillations. It was the nature of the electromagnetic theory of radiation that out of this theory came the idea of a speed of light. So James Clerk Maxwell, a great Scottish physicist of the mid to late 19th century, developed the theory of electromagnetic radiation, where light is just one example. And out of that theory comes the idea that light is an oscillation, and that the disturbance of that radiation inevitably travels at a large speed, the speed of light, 300,000 kilometers per second, and it cannot appear as a stationary phenomenon. So it's just built into the theory of light that it travels at a particular speed, a universal speed. Okay, thanks for that question and for all of them, and to Matthew and Alexander for facilitating the session. And we'll be back. I think we've already announced the next session next week at an earlier time slot, but we'll be back with you next week. Thanks for your questions.